Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why sometimes a simple idea seems to lead to really complicated results? Or why even when you think you found something important, it doesn't quite work out the way you expected? This new psychology paper dives deep into that exact puzzle, looking at how we use statistics to understand relationships between things. So the big question this paper is tackling is about how we look for interactions in our data. Think of it like this. Usually in science, we look at how one thing, like stress, affects another thing, like how well you do on a test. But sometimes the effect of stress might depend on another thing, like how anxious you are. That second thing, anxiety, is said to moderate or change the effect of stress. In statistics, we often try to model these interactions using a specific mathematical trick, a product term. But what if the real world isn't so neat and tidy? What if these interactions aren't exactly a simple multiplication, but something more complex? This research suggests that our usual way of looking for these interactions might be messing things up. Sometimes making us think we see something that isn't really there, and other times making us miss things that are. The researchers here notice that in psychology we really like simple models. We want our theories to be easy to understand, and a big part of that is how we look at relationships. When we talk about an interaction, we're saying the effect of one thing on another depends on a third thing. For example, maybe studying more helps you get better grades, but only if you are also getting enough sleep. The effect of studying depends on your sleep. But when scientists model this, they often use a product term, like studying multiplied by sleep. The problem is, the paper argues that conditionality, the idea that an effect depends on something else, doesn't automatically mean it is a multiplication. There are other ways relationships can depend on each other, like stepwise changes. Imagine this. The paper shows 3 ways relationships can be non-additives, meaning they aren't just simple adding up. Picture a simple interaction as a gentle slope that changes direction. Then picture a non-linear main effect, where one thing just goes up and down in a curvy way, even without the third factor, and then picture a stepwise effect, where the relationship suddenly changes at a certain point, something you might see if you are looking at a threshold. The issue is, scientists often assume the first one. The product term interaction is the only way to look at these complex relationships. This paper says that assumption is causing major problems. To see how big of a deal this is, the researchers did a quick look at some recent psychology papers. They found that a huge number of studies, like 77.2%, were looking for interaction effects. But here is the kicker: none of them explained why their interaction had to be a simple multiplication. Most just used that product term. This tells us that scientists are really interested in these complex conditional effects, but they're all using the same mathematical tool, the product term, even when their theories might suggest something different. This is what they call a specification crisis, a mismatch between what we theorize and how we model it. Let's look at a real example they analyzed from another study. This study looked at how calling that feeling of purpose at work affected workaholism, and how that relationship might be changed by obsessive passion. The original study found a significant interaction, but when the researchers here reanalyzed the data, they found that other ways of modeling non-linear effects actually explained the data better than the simple interaction model. Even more interesting, when they used a sophisticated method called MARS that can detect stepwise effects, it found a specific threshold for obsessive passion that impacted workaholism. This suggests that the original interaction might have actually been a stepwise effect that the standard product term approach missed or misrepresented. So they designed 2 main studies to test this. Study 1 asks, can nonlinear relationships, where one variable just curves, trick us into thinking there's a real interaction when there isn't? And study 2 asks, if there's a real interaction, but it is not a simple multiplication like a stepwise change, will our standard models miss it? In study 1, they created data where one variable had a curvy relationship with the outcome, but there was no actual interaction. Imagine you are plotting points on a graph, and they make a nice curve, but there is no evidence that the curve itself changes based on a second variable. Then they analyze this data using the typical linear models with and without an interaction term. And here is what they found. Across many different curving shapes, they saw that a significant interaction term popped up way more often than it should have. That fluke-o-meter reading, the p-value, was often lower than 0.05, meaning scientists might report a significant interaction that is just a statistical accident caused by the underlying curve. This happened even when the 2 predictor variables were completely unrelated, which is super important because it means it is not just about variables being correlated. The curvy relationship itself was fooling the interaction term. When these spurious interactions showed up, they usually had very small effect sizes. This is a big deal because in psychology, we often see interaction effects that are small and hard to replicate. This study suggests that some of those replication failures might actually be researchers finding statistical artifacts from non-linear relationships instead of true psychological interactions. They also checked how well these models generalized to the real data. For monotonic curves, those that just go up or down the interaction model didn't add much. But for non-monotonic curves, those that curved back and forth the interaction model did seem to capture more of the overall pattern. But at the cost of potentially overfitting, meaning it might work well on the specific data you have, but less well on new data. So, study 1 showed that we often get fooled into seeing interactions when the real culprit is a simple curve in the data. This leads to false positives finding something that isn't there. It is like seeing faces in the clouds when there are no actual faces. And this happens even when the variables are totally independent, ruling out the simple explanation that it is just due to correlation. Now, study 2 flips the script here. They created data where there was a genuine conditional effect, but it wasn't a simple multiplication. Imagine a staircase where the relationship between two things changes dramatically at certain steps. For example, maybe your mood improves with exercise, but only if you exercise for at least 30 minutes. Before 30 minutes, there is no effect. After, that is a stepwise effect. They created different types of these stepwise patterns. In some, like a mild V or strong V shape, the relationship between two variables changed in a way that a simple product term just couldn't capture. And what they found was that when the conditional effect was a smooth monotonic change, the interaction model did okay. But when the stepwise shifts were more dramatic or non-monotonic, meaning the relationship changed, then changed back, or changed in a more complex way, the standard interaction model completely missed the boat. It would report very small R2 values on the sample. And even worse, lots of negative R2 on the population level, indicating massive overfitting and very poor generalization. The simpler model, even though it didn't include an interaction, sometimes performed just as well or even better because it didn't try to force a multiplicative structure where it didn't belong. Study 2 revealed that our standard interaction models are often blind to genuine conditional effects that don't follow a multiplicative pattern. This means we can have real interactions happening in the world, but our statistical tools are missing them entirely, leading to false negatives. It's like having a locked door and only having a screwdriver when you need a key. So, bringing it all together, this paper lays out a serious problem. The common practice of using product terms to model interactions is a double-edged sword. It can create the illusion of an interaction when there is just a curve in the data, study 1, and it can completely miss real, non-multiplicative interactions, study 2. This isn't just a statistical quirk, it has huge implications for how we build theories in psychology. If we're finding interactions that aren't there, or missing ones that are, our understanding of human behavior will be fundamentally flawed. What is the solution? The researchers suggest that instead of automatically defaulting to multiplicative interactions, we need to be much more explicit about the functional form we expect based on theory. If you predict a stepwise effect, use piecewise regression. If you suspect a curve, use polynomial terms or more flexible models like generalized additive models. GAMS or multivariate adaptive regression splines, MARS. They emphasize that researchers need to justify why they're choosing a specific model rather than just following convention. And this really hits home for me. So often in science, we're trying to explain complex human behavior, but if our tools are systematically misleading us, then we're not really explaining anything, are we? We're just creating a story that fits a statistical artifact or misses a crucial part of the picture. The paper's title says it all, anything goes, because without a clear, theory-driven model choice, statistical interactions become a bit of a free-for-all, where we can find or miss almost anything. This study is really strong because it uses simulations to clearly show these problems. They're not just saying this might happen, they're demonstrating it under controlled conditions. The fact that they found these issues even with independent predictors in study 1 is incredibly compelling, as it shows the problem isn't solely due to correlations. However, like any study, there are limitations. Study 1 only looked at 6 specific nonlinear relationships and 2 predictors at a time, while real psychological research often involves many more variables. They acknowledge that in more complex scenarios, these issues could be even worse. Study 2 also had to make some simplifying assumptions to create its stepwise patterns. Ultimately, this paper is a powerful call to action. It's asking us to think more critically about our statistical models and to align them carefully with our theories. Instead of just plugging in a product term and hoping for the best, we need to be deliberate and justify our choices. This can help us avoid drawing false conclusions and ensure that the complex interactions we observe in the real world are actually the ones we're detecting in our data. What do you all think? Have you ever had a statistical finding that felt a bit too good to be true, or one that just wouldn't replicate? Let me know in the comments below, and if you found this breakdown helpful, please give this video a like and subscribe to RUBIN'S Mind Lab for more explorations into the fascinating world of psychology. See you next time.